What I'm going to present is a little R package we put out actually yesterday. For now it's on GitHub. I will show you how to download it and you can have a look at it and, I don't know, put in some issues when you find bugs, which you for sure will because, well, it's coding, so there will be bugs all over the place. For now, I'm just going to start and give you a little story how we actually came up to build that package because it's kind of not so trivial, you know. The first talk was very straight to the line and had a use case, and we actually don't really have a real-world use case, so I'm going to bring some kind of story how we came up with the package. The first thing, who we are, I guess Elda said at the beginning, we're going to have some time to talk about us, and this is what I'm going to do. First of all, you have a nice little GIF there because we really like GIFs and we wanted to implement them in the presentation. This one shows you how you can direct yourself to the web page in case you want to stalk us or something. As Sebastian said before, we're a little consulting company for data science. What we actually do is we kind of implement all kinds of machine learning solutions and deep learning solutions for our clients. We have offices in Frankfurt, Zurich, and Stuttgart for now, and Vienna as well. We have a lot of clients, and I guess they're all very happy with our work. And we advise them and implement solutions for them with the technologies our expertise lies in, which are, for instance, here R, Python as well, H2O, TensorFlow, Spark, and also Dataiku, which Sebastian pitched before. So this is what we're basically doing. For now, we have like 25 plus programmers. So we're a pretty small company, but we're also growing. And as you will hopefully think after the talk, we do really cool stuff. So before I actually start introducing the package and what we did, I'm going to show you how we got there. And I will do that by outlining the workflow every data scientist faces. And I guess you guys said it before, you're dealing with messy data, and that's the same thing we're doing as well. Whenever we start a use case or any kind of project with any of our clients, they're not necessarily data scientists, right? So what happens is they give us data that looks very crappy at the beginning and is very, very messy. And we need to come up with some kind of ways and a lot of code in order to clean the data up. And we do that basically at the very first day when we get the data. We load the data, we import it, we explore it, and so on. The next step in our workflow is the data preparation, you know? So a lot of times, for instance, when you look at time series, like financial time series or something, you have weird bumps in there. Like consider the financial crisis or something, you know? So quite often your time series do some really weird stuff that you not necessarily want to teach your machine if you're training one. So in that sense, you need to do some data prep, you need to smooth it, find outliers, and so on, and also do some feature engineering. Feature engineering is a very detrimental part where you actually just transform features in a way that they help your model performance. There was a professor who once said to me that if the world would be, he was an econometrician because my background's also in econometrics, and he said that if the world would be linear and you would only need to include linear variables in your model, then you wouldn't need an econometrician, and that's very true. And in order to cover stuff like that, like non-linear effects or whatsoever, you need to somehow build cool features. You need to do feature engineering, match features, transform them, whatever you like. The next part is the feature selection, and this is where the package comes in a second. The next part, feature selection, is very, very important for actually training a machine because you need to somehow figure out what kind of features or what kind of effects are important for any kind of prediction or forecasting problem that you want to solve. If you want to solve anything or if you want to train a machine, you basically do that by giving specific information to your machine. And so in order to actually give the right information, you need to have some kind of way to discriminate between the features or the variables or the information you feed to the machine, right? So in order to figure out relevant predictors, maybe one variable is more important than the other or so on. Or also in order to figure out the right transformation, right? Consider the feature engineering step. You build polynomials of one feature up to the order of, let's say, 10. But how the hell are you supposed to know what kind of order you need to put in your polynomial? In order to do all of that, we use feature selection. Once that is done, so basically everything what I'm telling now is happening after the package, you start somehow deploying your model, right? So you're trying to figure out what kind of model to use, you're selecting the algorithm, and you're choosing maybe also what kind of algorithm to use. At the very beginning, you might run some kind of ensemble, some cool machine learning algorithms, or very, very fancy deep learning stuff. Quite often, it's actually a linear model that performs really well in the first stage, but I guess most people working with like machine learning models know that linear models are performing really well, unfortunately. And the next step, which is not so important for that part, of course, is the deployment and the monitoring. I got to be honest, because I wanted to cover the entire workflow, and deployment and model factory are not really part of the talk, but this slide looked so nice, and I actually stole it from another presentation. So we have like all the steps, right? OK, so I'm going to be talking the rest of the time now about feature selection. And I'm not sure how many of you actually ran into a problem where you have way too many features for way too little observations. But we run into that all the time. The first time I actually got a use case, it was some financial KPI forecasting. And I have absolutely no idea about finance, about accounting or controlling or whatsoever. So what I basically did was I had a bunch of features, a bunch of accounts that made a lot of sense to an accountant, but not to me. So I started trying to figure out a data scientist's way of discriminating the accounts to figure out which ones are important. And this is exactly why feature selection is very, very relevant in the early stage of machine learning, right? Because if you have too many features, like I did with all the accounts, I had no idea which ones to use. And if I would have put in all my accounts, and let's say I have like 200 observations, but 2,000 accounts that I have no idea what they actually mean, then I'm not going to be able to either identify the model. If you think like an OLS algorithm or something, if you feed it 200 features and you have 200 observations, it doesn't really work. The other part is, I guess we all know that the right combination of features is actually doing the trick, not so much the algorithm, right? Especially those people who come from, like, let's say, econometrics or empirical economics or something. They know that it's most of the time, it's not really the algorithm you choose to solve your problem, but it's the features you put into the model to learn. And the other part is, obviously, features are, and I said that before, the features are everything, all the information you give to your model, right? So you want to train a machine, let's call it a machine for now, but we all know it's some lines of code, but let's call it a machine. You want your machine to learn to, let's say, predict some target or forecast something. And what you do is you give it features, and those features are the only relevant information that the model has. So the model can only choose from the information you give it to. And because of that, you want to make sure that the information you feed to your model is actually relevant. In basic or in classical econometrics, there's a very, very nice theory of this omitted variables bias, right? You're trying to identify some effect, but for that, you need to make sure that you include all the relevant predictors. Otherwise, you're not going to cover all the information you want to cover. And this also applies to classical machine learning problems. You want to feed it all the information you have and all the information it needs, but nothing more than that. So how do we actually select the features? And this is where our package comes in the end. And you can see here the essence of the slide is the last sentence. And I mean, there are a couple of ideas how you can select features. One is, of course, you have to, I could have started, I had 2,000 accounts and 200 observations. I could have started putting all the possible combinations of accounts together, running some models and trying to evaluate them and see whether they're interesting or not. The next thing I could have done is I could have looked at bivariate correlations. I could have said, like, oh, this account correlates with my target, so probably it's kind of interesting. The other thing I could have done is I could have written a small loop and would have done the following thing. I would have basically split my data into train and test. I could have put all the feature combinations together many, many times over and over again, and I would have tested Okay, so this feature combination learns the machine in a particular way in the training set, and then I could have tested it on my test data. This is, of course, here you see our non-subjective assessment of the idea, a bit cooler than all the rest. But now you don't have to do that anymore, because obviously now our super cool package comes in, and obviously this is not biased, this is purely objective what I'm saying. So if you want to look at the package, you will find that it solves all the problems you ever had. No, probably not. It hopefully runs through, so that's the state we're in. The thing is, in research or in academia or machine learning in general, you have, amongst others, you have two main methods to filter out features. I briefly described some of them, like for instance manually testing, looping over and stuff like that, or using bivariate metrics. You can fit them into two groups. The first one is the filter methods. Filter methods are very, very simple methods where you basically apply some kind of bivariate metric. You look at the distribution of, for instance, the target and your features, and you figure out which ones are kind of important by, let's say, looking at correlations or any kind of stuff that is somehow bivariate in any sense. Obviously, this has some advantages. The way I said it, the way I phrased it, you realize that it was quite, that is quite computationally cheap to actually do that. Looking at correlations, if you have a couple of features, it doesn't even take a second. It's no problem, right? The other thing is, if you do that basically on your training data set, it also doesn't give you any chances of overfitting. So that's something that's very nice. The other thing is, and I'm not sure whether it's always an advantage or not, it's completely independent of your model algorithm, right? So you filter everything, you figure out some features, and you say, okay, they were correlated with my target, so why not use them, right? So it doesn't give you any kind of bias. Like for instance, if you look at the random forest, it also does feature selection, but it does so based on an algorithm, and it says these features are important for tree-based algorithms. The disadvantages, of course, and I'm going to really dig a bit deeper with them because they're basically the reason we developed the package. The disadvantage, and this is a very, very big disadvantage, what you actually get is if you, for instance, look at correlations, you get a bunch of features that are correlated with your target, right? But the problem is, most of the time, they're actually redundant. So you're getting redundant features. You're getting features that are not very exclusive to one another. And so in the end, you get basically a bunch of features out of there that more or less cover the same information. And that's also something you don't want to have. The other thing is you don't actually look at the entire feature space. You know, you have a lot of information at your disposal, and you choose to look at only one at a time. So that's also something that is quite a weakness of these filter methods. Then you will have another big branch of filtering or feature selection methods, which are wrappers. Wrapper methods are basically what they sound like. So you kind of write a loop, more or less, and you wrap over everything you have. You loop over everything you have, and you basically iteratively search for the best feature set. This is something, of course, it's cool because you get to program a loop, and that's always a lot of fun, but also allows you to have a very granular selection of your features, and you look at the entire feature space. You know, other than with filtering methods, you're looking at the entire feature space, which allows you to have some kind of wholesome consideration of the entire space. Also, wrapper methods turn out to be very, very good at finding the relevant features. Finding the relevant features, of course, is something very desirable, but at the cost of being very, very computationally expensive. You can imagine if you have 2,000 features, like in my example before, you build little feature sets, and you're trying to cover all the combinations, right? So all the combinations of features put together in feature set of, let's say, 20 features at a time or something, you're going to wait forever until even an LM is running, right? So that's taking very long. And the other problem is, if you do that, what you're intrinsically doing is you're testing your feature set, or you're evaluating your feature set based on the performance of the test data, right? So what you're kind of doing is, of course, you do a test train split, but what actually happens is that you choose the one that fits the test data the best. So you're totally overfitting the test data, which is also not a good idea. So this is something that we didn't want to have. And in order not to do that, we came up with a very good idea. And this is actually a true story. So as the President of the United States, it sounds weird, but unfortunately it's true, says here in his doctrine, we should all use component-wise boosting. And this is what we're doing. So basically, we're leveraging component-wise boosting in order to avoid all these problems. We're trying to avoid overfitting, of course, because it doesn't help us if we select features that totally overfit the training data, right? We also don't want to have it too computationally expensive. Well, okay, this is still a cost that we still need to bear somehow, but at least we're not overfitting. And also, we want to consider the entire feature space. And this is what we're doing by applying this very clever method from this guy here. Before I really dig into the algorithm we programmed, I'm going to give you a very brief introduction in what component-wise boosting actually does. Component-wise boosting is a gradient boosting algorithm that is basically an ensemble. And what it does is, and this is very, very smart, it allows you to discriminate the features by the relevance. So this is very cool. This is exactly what we need. And I have some pseudocode here for you guys so you can see what it does. So you can imagine it as a sequential ensemble. So you have m-stop iterations. You have a lot of iterations where you basically do the same thing, however, on different data. And what happens with component-wise boosting is now that in every single iteration, you take one feature at a time out of the entire feature space. And for every single one of these features in your feature space, you build a base learner. And the base learner is a very, very simple model. In, for instance, linear component-wise boosting, you're using an LM. For every single feature, in every single iteration, you build a linear model, a very simple one. You can do that with trees, you can do that even with fancier stuff, but we're doing it with linear models because it helps us not to overfit. Because I guess you guys can all imagine if you have a forecasting problem and you run an LM with only one feature, I mean, there's no way to overfit, right? So that is helping us to avoid the overfitting. What actually happens is in every single one of those m-stop iterations, we build a base learner for all of our features. So let's say we have 200 features in our feature space. Every single iteration, we build 200 linear models with only one feature. What then happens is we're looking at which one of those base learners is fitting the data the best. And this base learner, the one that fits the data the best, is going to be added to our final model. And we do that, we add the best base learner to the final model, and we do that a lot of times. So we do that m-stop iterations. So in m-stop iterations, we have chosen the best base learner. What happens after we chose a base learner is that we somehow trick the data a little, because we're looking at what kind of errors were we making, what couldn't we explain in one iteration. So we're trying to adapt the model fitting procedure by updating our sample weights. We're weighting the sample in order to give those observations that we couldn't really explain, where we had a big error. We weight them a bit more so that in the next iteration, our algorithm can learn the observations where we didn't really fit well. We do that a lot of times. We do that m-stop times. And then in the end, we will have some kind of final model with only the base learners that were chosen in the periods. So this helps us because imagine that we have 200 features. And in every single iteration, we build 200 base learners. What then happens is, in the end, we might have selected in every single iteration only one base learner. So that means that out of the 200 features, only one base learner, so basically only one feature, survived the entire procedure. And in the end, our final model consists of only one, of only one base learner. And so that basically means that it's more or less incremental in this procedure that we somehow have a very granular feature selection, right? So this is a very, very smart idea, and kudos to the guys who actually came up with that and implemented that. And we're basically building our entire algorithm, the entire algorithm we designed, we build it around this idea. So our goal with the next algorithm was we need to somehow bring that component-wise boosting in a framework where it allows us to do exactly what our bounceR package is doing here. I mean, a lot of data that or a lot of features that we feed into our algorithm is actually noisy. And we want our bounceR package to kick it away like that dude does with his nunchucks. And a very, very important part is, I mean, we couldn't visualize the non-overfitting in a GIF, but you have to imagine that we're doing that without overfitting. And that was our goal from the very beginning. And I guess you looked at that guy punching the noise variables for long enough now, so I'm going to continue. And we came up with an idea where we basically leverage component-wise boosting in order to help us to select the features. What we're doing is we're building a very, I mean, it looks a bit complex, but it actually is not. We're building some kind of ensemble, and we're stealing the ideas from component-wise boosting and also from neural networks. We put them all together in some kind of ensemble that we built. You can consider the following thing. We have here nothing else but the data. And then we do the following. We build an ensemble of n rounds. So for n rounds, we do exactly the same thing. And I'm going to describe to you now what we're going to do in each of these n rounds. In each of these n rounds, we're going to initialize a completely random stability matrix. This stability matrix gives us nothing else but the relevance distribution for each feature, right? So we're looking at the features and we're saying, oh, this feature might be relevant, or this feature might not be so relevant. But actually, it's totally random, so we just initialize it. And then what we're doing is, over the course of n models, so let's say we run 10,000 models, we run 10,000 component-wise boosting iterations, and we run 10,000 component-wise boosting models with the data. And every single time we're checking, okay, this feature potentially comes into the component-wise boosting, but it doesn't come out. So that tells us that it's not a very important one, right? So if we know that a particular feature didn't survive the component-wise boosting, we're going to update the matrix, which is visualized by this thing blinking. It's also a GIF, so. And we continue to do that. And then, on the other hand, when a feature goes into a component-wise boosting and it does come out, that tells us that it could be potentially important. So we adjust the score in our stability matrix, which is always there to basically give us some kind of feedback on whether or not a feature is important. We do that a lot of times, and we do that this entire procedure of initializing a random matrix also a lot of times. So by the end of the day, or by the end of this procedure, which does not take a day, we have a lot of stability matrices that were updated over the course of a number of models. And then what we're doing is we're looking at the aggregate of these matrices. So we're kind of putting all the matrices together, and we're thinking, okay, so in each of those iterations, or in each of those n rounds iterations, we receive the stability matrix and we somehow aggregate them. We do that by simple averaging. So at the end of each of these runs, of each of these n rounds, we basically get an updated stability matrix. And in the stability matrix, for every single feature, there's some kind of relevant score. And we can now average it basically across all our different stability matrices that we have. So this is basically the very, very simple visualization of this entire thing. If you want to get it a bit more technical, we have here some of the pseudocode as well. So what we actually do is basically exactly what I just described, but if you want to have it visualized, because I prefer this way of visualization, because the other thing is a bit, let's say, weird to understand, but it looks cooler. And if you want to have a look at it, you can obviously do that. So it's very simple, actually, the algorithm. It relies on, obviously, component-wise boosting, because I just pitched that idea. And also, it kind of relies on this very, very clever idea of backpropagation from neural networks, where we initialize a random distribution, and then we update it over the course of a lot of models. So this is what we're basically doing. And at the end, we just get an average stability score distribution out of these matrices. And based on this now, we can somehow say, okay, in all our basically simulations, we can say that particular features always turn out to be very, very important, right? Because if we do 1,000 of these n rounds, so we have 1,000 of stability matrices, and in every single one of them, one particular feature is always on top of the matrix, is always very, very important, and we can conclude that it seems to be very relevant, right, for the case. And this is our idea of solving this feature selection issue. And the important thing is, you can do that totally on the training data. You don't have to use any test data for that. And another cool feature is that with the linear component-wise boosting as a weak procedure, basically, inherently in the ensemble, you don't really have the problem of overfitting, because what you're actually doing is you build a lot of linear models with only one feature, so there's no way of overfitting. And this is our little approach to feature selection. We're actually applying it all the time, and it turns out to work really well. And we thought, why not actually give something back to the community? Because, I mean, we're all using open source software mainly, so why not give something back? We put everything into a nice little package. And we put everything into a nice little function that has the very, very catchy name feature selection. And you have, of course, you need to feed the algorithm or the function a few things. And probably if some Python coders are in here, you're probably going to hate the syntax, but I'm really sorry, because this is kind of standard R layout. So the first thing you do is you obviously need to feed some data, because, I mean, every single algorithm needs kind of some data, right? And then you basically just give the name of the target column, and what's going to happen is we're taking the target column and we're trying to figure out what features in an entire data set are important for our target. You can give it an index, is not so important, and now comes the important part. This is the selection control. These are basically your tuning parameters for this algorithm. You can manually adjust how many rounds you're running this entire ensemble. You can manually adjust how many models you will run in every single round. You can manually adjust how many P features are you going to give every single component-wise boosting algorithm, because you might not want to give all of them to it, just a piece, every single time a random sample of the feature space. And then what comes here is you can kind of choose how to update your matrix. You can basically give a reward for surviving the component-wise boosting, or you can give a penalty for not surviving it. And this is how you can manage to somehow update the stability matrix over time. If you want to, if you're like into that kind of stuff, you can bootstrap the data if you want to. So for every single of those component-wise boosting iterations, you can give another bootstrap sample to it. You can adjust the boosting whatever way you like. You can also add some early stopping. This is totally up to you. And you can run it on multiple cores. And this is done for Mac or for Unix and Windows as well. So this is the very simple setup. I'm pretty sure none of you are actually trying to type that in right now. So I'm not going to spend so much time on that. But you can actually use it already. The package is hosted on GitHub. It's publicly available. You can simply install DevTools, which you need by now, because this is only a development version, and it's not listed on CRAN, because that actually takes a very long time, and you need to somehow build very reasonable documentation, which we're kind of doing, or kind of did, but there still is some work to do. You can simply install the package, you can look at it, and I'm pretty sure you will find some bugs and some issues that we need to work on. And so what you can do is you can just give us an issue, or set an issue in GitHub, and we will start to work on it in a reasonable time, I guess. So this is how you can interact with the package or with us. You can obviously look at the repo, and also all the memes and GIFs that I showed you so far are included in that repo. So even if you just want to have a laugh, you can go there. The content of the package is very, very simple. We put a nice little simulation function in there, so you can test the package, you can simulate your own data, and then you can run our different algorithms. One thing that I talked about at the beginning is this filtering issue. We also implemented the standard filters. So We're not really using them so much, but we were thinking that it could be like a wholesome idea to also put them in, and you can choose between 2 different filters in this one. Then here comes the feature selection function, which essentially is the heart of the entire package. So if you want to really learn like what we're doing with feature selection, you can definitely take a look at this one. And then there's some convenient stuff that you can do, like typical methods like printing, plotting, summary, and so on. And obviously what we also implemented is that you can have a look at like the optimal formula that our program suggests with the builder function. For now, this is the end. If you're interested in that stuff, you can talk to us. You can actually just send us an email, or you talk to us right now. And I guess other than that, the GIF is going, I'm too fast, because now there comes a joke. The joke is here. So you can now all drink your beer. And thank you very much for having us. Thank you very much for the attention. And hopefully you'll find some bugs and help us improve the package. Thank you.